Here's page 2 of your gas equilibrium notes. Maybe not one of the more important things here, but this is Kc versus Kp. So your equilibrium constant, which remember is your products over your reactants. It's the ratio of your products over your reactants at equilibrium. So what is that ratio of this over this at equilibrium? That's your K value, that's your equilibrium constant. We'll do lots of different Ks. So you might see Keq, you might see Kp, which means K in terms of pressure. So it'd be pressure of this squared over pressure of this cubed over pressure of that. You might see K in terms of concentration. It would be molarity of this squared over molarity of this cubed over molarity of that. Eventually we'll do K in terms of acids, K in terms of bases, and Ksp, which has to do with dissolving. So there's going to be a lot of different Ks. They're all the same thing though. Always products over reactants. Remember your K value only includes gases and aqueous things, no solids or liquids in your K expression. All right. What is the size of K indicated by the equilibrium system? If something has a big K value, so if the K value for this was big, it'd mean there's lots of those compared to here, because your K value is your ratio of products over reactants. So a small K means more reactants than there are products at equilibrium. All right. We can interchange between K in terms of pressure and K in terms of C. And here's, I don't want to talk too much about this, but if we think about PV equals nRT, if I solve for P, so divide by V, get V over here, volume. Well, moles divided by volume, moles divided by liters is molarity, which is your concentration. And pressure, so we're gonna kind of relate pressure to concentration in terms of gases. Pressure to concentration in terms of gases. There's a little formula right here. So find Kc at this temperature. If at equilibrium, we have these molarities. So if we do that here, let me move this up just a little bit. So if we go Kc equals the molarity, it's K in terms of concentration, molarity of NH3, which is 0.031. So this is 0.031 molar, so 0.031 squared, because it's got 2 in front of it, over molarity of NH2, which is 0.85. So 0.85 to the first power times H2. Oh, sorry. Yeah, H2, 0.0031. This is 0.0031 squared. So if we get our K in terms of concentration, it is 3.8 times 10 to the 4th. Very big K, which means it favors the reactants more than, the products more than the reactants. Okay, there's our K in terms of concentration. K in terms of concentration. Very rarely do we do this, okay, just so you know. But we can go from Kp to Kc by using this equation. By using that, our K in terms of pressure equals our K in terms of concentration times RT to the delta N. This delta N is our change in, that's supposed to be an N, change in moles of gas. Change in moles of gas in our reaction. Products minus reactants. Change in moles of gas. Okay, I'm going to get rid of this stuff here just for a second. This doesn't matter because this is just our endothermic exothermic stuff. So if we think about this, if we want to get our Kp equals our Kc, so 3.8 times 10 to the 4th times R, which is 0.0821, times T in Kelvin is 400 degrees Kelvin, remember it's plus 273, to the change in moles power. Well, there's two moles of gas here and 4 moles of gas there. 2 moles to 4 moles. 2 moles minus 4 moles. 2 moles, we're going down by 2 moles as the reaction goes, so it's to the negative 2 power. So that change in moles is that power there. This is not something we do very often, but our K in terms of pressure, and if we do that, is 35. Okay, so sometimes we have to translate between those two things. Not very